Hi, this is Big Tuition, and this is a quick review on the chapter of complex numbers. So, complex numbers are basically a generalization of the real numbers that we usually encounter, and it is denoted by z usually, unlike how we denote our our real numbers by x. So, complex numbers are represented in the x plus iy. This is known as a Cartesian form because there are many ways to actually represent these complex numbers. So in this case, x and y are both real numbers, and I equals to square root minus 1. I know most of you probably did not encounter this kind of imaginary number before, or this I is an imaginary number. And we know that in the past we always say that we cannot square root a negative number. But in the case of complex number, we kind of bend the rules a little bit. Instead of saying that we cannot square root a negative number, we assign the square root of the negative number as a imaginary number I, and then we just write it as a sum of the real component x and the imaginary component y. Okay, so x is known as the real component of the imaginary number z and can be written as real part of z, whereas y is known as the imaginary component of y and can be written as imaginary z. Note that x and y are both real numbers. It's just that y must be multiplied by an imaginary number. Okay? X and y by themselves, they are real. Okay? Just don't get confused. If y is equals to 0, the complex number is simply a real number because it has no imaginary component. If you are watching this video after you have seen the vector component, you can think of the imaginary component as a different axis, as like maybe a y direction and an x direction. Okay, so if y is 0, that means your complex number is only in the real axis. So you only have a real component, therefore it's a real number. Okay? So in this aspect, because when y equals to 0, we get real number, we can see that real numbers are a special condition, like a special set of complex number. So we can actually write all our real number in the complex form. It's just that it will be like x plus I times 0. Yeah, then it's just real number, right? So for like real numbers, when we say that two numbers are equal, 10 equals to 10, we just say that, oh, the numbers are equal, therefore they are the same. But in the case of a complex number, you need both the imaginary and real components to be equal before we can call them the same. Next, we see that we introduced this thing called a conjugate. Alright. So the conjugate of a complex number, don't have to worry what it means. It's just you switch the sign between the imaginary component. So if let's say you have an imaginary component that is x plus or minus y plus y, the conjugate is x minus iy, and vice versa. This conjugate is denoted with a star on the top right of the complex number. So the normal complex number is z, and the complex number is z star. And by the way, just notice how I'm writing z. Actually, if you are not writing z like this, I would highly recommend you to do something like this, because there will be a lot of times when you make careless mistake and you write z then you get confused with a 2. Okay? So anyways, back to complex numbers. When we multiply a complex number with conjugate, you get a real number x squared plus y squared. So it's something like x plus iy multiplied by x minus iy, and then you try and work out the rest. We know that I square equals to minus 1. So you use this, go and try this if you have not already done something like this. Knowing that a complex number multiplied by its conjugate gives us a real number, knowing this fact is very useful for us when we try to manipulate complex numbers later on. So just like real numbers, we'll do operations on complex numbers, and that we begin with very basic ones like addition and subtraction. The tip for operating with complex number is to just expand into the Cartesian form, where you have the real plus I imaginary component. As an example, we can look at addition and subtraction. We have the first imaginary number plus or minus the second imaginary number. We can just add the component, and we can just add each of the component up. And in case you are wondering, this looks like vector addition, and it is basically vector addition. Complex number is actually very closely tied to vectors, the basic parts of vectors, not the planes and lines. Complex, you can think of complex numbers as basically numbers in a 2D vector space, if that helps. So this is, well, maybe it helps you grow your intuition for a complex number. Next, for multiplication, again, we should try and write it in terms of the real and imaginary to start off with. Later we learn other forms, and it might be easier to do multiplication in other forms. But for starter, we use the Cartesian form with x plus iy multiplied by x2 plus iy2. We see that the two components of the x multiply, this is basically rainbow method. Then we have x1 plus y2. Then we have y1 times x2. And then we have y1 times y2. Yeah, this is a rainbow method, if this sounds familiar. Like, remember when we have to do a plus b, c plus d. Okay, something like that. And after we expand this multiplication out, we notice that I squared is basically minus 1. So this becomes negative. And we group the terms together to give us a new complex number. In the case of division, it is probably the hardest because you need to make the denominator go away. When we do division, we see that the number below is a complex number. But when we do division, we want to end up with a single complex number. We don't want to have like a fractional complex number. Then that's not really doing the division, right? So to get a single complex number, what we do is we make use of conjugate. When we multiply both the denominator and numerator with the conjugate, we basically turn the denominator into a real number. Because, well, we see this on top here. We see this. When we multiply a complex number by its conjugate, we get a real number. In that sense, we can then work out the numerator as a single complex number by doing the multiplication here. Okay, this thing here. Essentially, the numerator will give us a multiplication and we are done with the division. But this usually is a little bit more complicated than multiplication because you have to do several steps beforehand and you have to deal with a possibly large number in the denominator. Alright. We saw how useful the conjugates are. We also need to investigate what are some of its properties. One is that conjugate of its conjugate just give back the original. This makes sense because it's like x plus y, iy. Then you conjugate becomes x minus iy. You conjugate again and it becomes x plus iy again. Conjugate of a conjugate give you back the original. If you have a real number, then the conjugate is equals to the original number. Because, well, I times 0 is just 0. So x equals to x. This makes sense, right? Next is when we have a complex number adding to its conjugate, we can get the real number. We can get the real component, but it's times 2. We can think of it as this is no need to think. You can just work it out. Okay, x plus iy plus x minus iy dot dot dot. Same thing for this. And then there's this, which is when your complex number is multiplied by its conjugate, you get the real number. And finally, when we have a addition of conjugates, when we have addition of complex number and we conjugate the whole thing, we can basically conjugate them separately and then add them up. This makes sense because we see that x plus iy plus x1 plus iy1 plus x2 plus iy2 conjugate is just equals to the right hand side. If you don't believe, work it out. Just work it out. Okay? Same thing for this. This one is probably the not as intuitive or obvious. It's important to know, and you can also just work it out. It's quite straightforward. So these are some conjugate properties that you will need to know for complex numbers. And give me 1 second. I'll go charge my Apple Pencil and I'll be back. Okay, hi, I'm back. So moving on, we have a short theorem called the conjugate root theorem. It says that if a polynomial with a real coefficient has complex roots a plus I, alpha plus I beta, alpha minus I beta is also a root. Okay, this is just a theorem. Try and remember it. If you find it hard to remember, we can take a look at quadratic equation. Remember, we have a quadratic equation. We always talk about b squared minus 4ac, right? This one must be more than 0 for it to have two real roots. But then you realize that now with the knowledge of complex number, we understand that when the discriminant is less than 0, technically we still have two roots, but the two roots will be complex, right? Now what happened is we have minus b plus minus square root. Let this be let's just say iy, because it will be a complex number, right? It will be in fact it will be imaginary because it's negative. And we see that here there's a plus minus. So basically it's alpha plus I beta, alpha minus I beta, both of them are roots. Okay? So yeah, the quadratic equation will be a fantastic example for the conjugate root theorem. Moving on, we have Argand diagrams. Because the complex numbers can be written as x plus iy, we can plot them on a Cartesian coordinate with x-axis showing the real part and y-axis showing the imaginary part. So in this example, we have complex number 4 plus 5i, and we can plot this point as a P on this Argand diagram. Okay? So if this looks familiar, this is actually basically plotting a point on the 2D vector space. Yeah. Next, we can see that plotting the complex number this way gives us new ways to represent a complex number. We can write it as a vector, OP, like this. Or we can write it in terms of a distance, an angle from the real axis. So angle from a real axis would look like this, right? We can write it as R with an angle. And this R with an angle is also known as the polar form of a complex number. Previously, we know that there's a Cartesian form, which is x plus iy. This is a Cartesian form. The polar form is represented using these two angles. There are these two values. One is the distance and one is the angle. The angle is basically Pythagoras theorem. It's like, well, magnitude of a vector, right? This is also known as the modulus of the complex number or the magnitude of the complex number. The counterclockwise angle from the x-axis is known as the argument. These highlighted things are all very important. These are all important terminologies that you might come across. And if you don't know what they're talking about, you might get your question wrong, or you might not even know how to start your question. So please take note of this notation. So this counterclockwise angle from the x-axis is known as the argument of the complex number. It's denoted as arc z. Z is the complex number. This can be calculated using trigonometry, where your angle is equals to arctangent of y over x. Okay? As the angles are cyclic, the argument is not unique, because we see that when the angle go through another 2 pi, we end up having the same angle, right? Practically the same angle. But because of that, the argument is not unique. We can restrict the argument to be minus pi to pi, and this is known as the principal range. Okay, this is known as the principal range. Another terminology, yes. Finally, we have the polar form, which is written in terms of the angle and the distance. So we have x equals to r cosine theta and y equals to r sine theta. And we can write the Cartesian form in terms of this. Yeah, this is the polar form. Okay, before we move on to any other forms, we briefly talk about the modulus since we use the modulus here. Okay, so the modulus is that we know that modulus of a conjugate equals to the modulus of the complex number itself. This is because if we plot the conjugate in the Argand diagram, right, we essentially just get a reflection in the x-axis. So I'll do a simple case of x plus y. Okay, so let's say we have a point here that is x plus y. X plus y, iy, okay? Its conjugate will have the negative y but have the same positive x. So this is the conjugate. This is z and this is z star. And in this case, it is natural that the modulus, which tells us the distance away from the origin, remains the same. Okay? And one thing to know is that this modulus z, right, is a real number. So real number, conjugate of a real number is just equals to itself. So actually this conjugate here does nothing. Okay? Another thing is that when we multiply two of the complex number together, we can take the modulus of two complex number multiplied is equals to the multiplication of the two complex number by themselves. So this is just you can show this by multiplying this form in this form, and you realize that because cosine theta plus I sine theta just doesn't give you a cosine theta plus I sine theta has a modulus of 1. Why 1? Because sine square plus cosine square give you 1. Simple as that, right? So that means the only thing that changes the length is the r here. And r1, r2 cosine theta 1 plus I sine theta 1 cosine theta 2 plus I sine theta 2. All this, when you multiply everything, you realize the only thing that matters is the r here. The two r's here. So actually, yeah, when you multiply two complex number together, your length is just the two lengths multiplied. And we can extend this to an even more general case where you have multiple multiplications and it's just the length to the power of n. Basically repeated application of the product property right above, which is this. Okay? So these are some modulus properties when it comes to complex numbers. Modulus here is just talking about the magnitude. Okay? Next, we have argument properties. The properties with the argument angle. We see that because of how this is theta, this is minus theta, so we can tell that the argument of the conjugate is the negative of the argument of the original complex number. So conjugate is reflection in the x direction, x-axis, in the real axis. So the angle is in the other direction, so it will be negative. One more thing is, this may not be super obvious, but when you have two complex number multiply with each other, the arguments add up. You can probably show it through like trigonometric rules, application of like trigonometric identities from like above here. You can probably show it, but it's just remember that the angles add up. And again, we can use a repeated application of this additional of angles and get the third property here. Alright, so some of the interesting discussion will be that we see that when we have the complex number multiplied by its conjugate, we can see that the argument gives you 0. And indeed, because we get a real number, right? We get a real number when we multiply the complex number with its conjugate. So we can show that in a different way. We can show it in a different way that we get a real number, because the argument will give us 0 when we multiply them. Next, the complex number I can be found in the Argand diagram at 0, 1, meaning that it has a modulus of 1 and the argument of pi over 2. When we multiply this any complex number with I, the modulus does not change, because we know that the modulus, according to this, the resulting complex number have a modulus that is the multiplication of the two modulus, and we know that modulus I is 1, therefore the modulus does not change, but the argument increases by pi over 2, not pi, sorry, this is pi over 2, another typo. This argument increased by pi over 2 as the argument equals to this. And that means multiplying your complex number by I is essentially a counterclockwise rotation by pi over 2 or 90 degree in the Argand diagram. So if I multiply this, if I multiply z with I, we end up with having a 90 degree rotation. This is I, z, like this. Okay? Here, just now we talked about how we need to use trigonometric identity to prove this argument property, right? So here is basically saying the same thing. By writing down complex number in their polar form, we can prove by trigonometric identity why the arguments are like this. So you can try it as a good practice. Finally, we have exponential form of a complex number. This is probably quite new to you. Euler formula. We can write EI theta as cosine theta plus I sine theta. And this looks familiar, right? Because this is essentially this cosine theta plus I sine theta. It's basically the polar form. So this is the exponential form. Okay, actually I wrote this here also. So we have REI theta. This is a exponential form, and using this form is much easier to see why we have modulus and argument properties. You can try and show it, but it's really very obvious. In fact, you can probably see it from here. You can see that R1, R2 get together, the modulus, therefore this is a new modulus. And because they are multiplying, by rules of indices, the angles will add up. And therefore, we have a total modulus of R1 times R2 and the total argument of theta 1 plus theta 2. Okay. And conjugate of a complex number can be represented as adding a minus to the angle in the exponential form. Okay, and with that we have basically summed up all the main key concepts in complex numbers. And here in this chapter I gave some recap question. Good to just look through lah. So how many forms of complex numbers did we learn? We have, well, pause the video for a while if you want to think about it, but we basically have 3 forms. Before we learn the Cartesian form, we learn the polar form and the exponential form. And how do we convert from one form to another? For Cartesian to polar form, there is here is through this. And if you want to go back, we just simply calculate what is cosine theta r, and that's your x, and sine theta r to get y. So it's quite simple to transfer from polar form to Cartesian form. For exponential form, we just apply the Euler formula here. Okay? So that sums up this chapter of complex number. I hope this was helpful for your revision. Okay? Happy studying!